Alright, well, I thought it'd be productive to make another video here. So, this is concerning some problems from, I want to say, week 7 and week 8 homework. This is about where we left off, I think. I don't remember. But find the multiplicative inverse of this and there. Now, this one's a little tricky. So if I try the direct approach where I put alpha equal to x plus the ideal. Okay, so I've got alpha cubed minus 2 equal to 0. Well, if I'm trying to find the inverse of alpha squared minus 2 alpha plus 1, I'm looking for a, b, and c rational numbers such that this product is 1. And, well, I mean, subject to the rule alpha cubed is 2, and alpha to the 4th is 2 alpha, things like that. And it's just not very easy. I mean, I can do it. I did it. Show you how I did it. So, of course, the one way to solve this is just basically by direct attack. This is what I want, and so multiply it out, then I can group together everything, the constant, the coefficient of alpha squared. We have a theorem which says that these have to be separately 0 because 1 alpha squared is linearly independent, because alpha cubed minus 2 is an irreducible polynomial, and as such these are linearly independent, as theorem you can prove. But anyway, so I mean, to suppose there was linear dependence amongst alpha squared, and a constant would be to find a lower order polynomial such that alpha was a 0, which would then contradict the alpha x cubed minus 2 being the minimal polynomial of the cube root of 2. But anyway, let me not get into the weeds there. Anyway, the long story short of it is I get these 3 equations and 3 unknowns, which I add and subtract and combine and eliminate and substitute, and after a little bit of algebra here, I get to a equals to 5, b equals to 4, c equals to 3, which shows me that, in fact, my inverse is 5 plus 4 alpha plus 3 alpha squared, which in the other notation is 5 plus 4x plus 3x squared plus the ideal. All right, it's this element in the factor group of the polynomial ring. But this is fine. But there is another way to do this, which is there's a Euclidean algorithm for polynomial division, and I'm not going to show you the details of that because it's kind of like, so this is a little bit, I mean, this is a reasonable, reasonable homework question. It's probably not a reasonable test question as such, just at least in the current iteration of the course, because I haven't forced a lot of homework problems that tell you about this, except perhaps this problem. But to be friendlier, I have to say use polynomial, the Euclidean algorithm for polynomials, and then it would be a less unfriendly problem in that regard. But there is something called the polynomial Euclidean algorithm, and if you do the analog of the Euclidean algorithm for polynomials by successive division, remaindering, and all that, you can find that there's this identity, in particular, minus 3x plus 2 plus x cubed minus 2, that product, plus the product of 3x squared plus 4x plus 5 times x squared minus 2x plus 1, well, that equals 1. Which is to say that x cubed minus 2 and x squared minus 2x plus 1 are actually, well, they're co-prime, you could say. Their greatest common divisor is 1, as it happens. But anyway, once you have this equation, it becomes easy, because if we're working in the polynomial ring, the polynomial quotient where x cubed minus 2, anything with that is that kind of multiple of that representative is 0. Well, this term drops out, and you're just left with this. And then, of course, we we find our answer again, right? Here it is. Here it is. This times that gives me 1. That makes this the inverse in that quotient ring. So anyway, yeah. So that one's not as good of a test question in some sense, because it just requires like a lot of calculation, however you slice it. Now, problem 79 part C, a little bit easier. Now, problem 79 part C would make a lovely test question because it's very simple and to the point, and if you understand the idea here, it's not bad at all. So, to find the multiplicative inverse of this in that quotient ring, I let my alpha be x plus the ideal again. The defining condition for the quotient ring is alpha cubed plus alpha plus 1 equal to 0. Notice that the presence of this 1 is super nice because that means we can rewrite it like this, and then I can rewrite it like that. And factor out alpha, well, whatever's here, this times that is 1. That makes this the multiplicative inverse. So, of course, mod 5, that's 4 alpha squared plus 4. There you go, multiplicative inverse, done. That took us all of a minute. So that's part of the reason there could be, 25 problems on your final. Some of the problems are like that. All right, so problem 80. You're supposed to decide, let's see here, you're supposed to decide what? Which of the x squared plus a in z5x are irreducible, right? So this is a quadratic, so to check irreducibility, actually that wasn't the problem. I don't have my, I'm sorry guys, I don't have the homework printout right in front of me. I think the question might have been, the question might have been which z5, well, let's just answer this question, whether or not it was asked. I can't remember. My bad. Sorry, guys. But how about this? z5x mod the ideal generated by x squared plus a, right? Is it a field? Right? So that question is it's closely related to the question, is x squared plus a as a polynomial in z5x, is it irreducible? See, if x squared plus a is irreducible, then that means that this is a maximal ideal, and that implies, of course, that the quotient of a commutative ring by a maximal ideal is a field. Now, if x squared plus a has a 0, then this is not going to be a field. All right? So like x squared plus 1 factors. So definitely, if I mod by x squared plus 1, this is not a field. This is something else. Now, number 2, if we had x squared plus 2, then you plug in the 5 different values, 0, 1, 2, 3, and 4. Now, of course, you could put in minus 1 instead of 4, right? You could, in 3, we could have done minus 2 instead if you like, because we're working mod 5. But anyway, the point is the 5 values of this polynomial over z5, they're all non-zero. Therefore, this is irreducible. Consequently, that quotient that I was talking about up here, therefore z5x mod the ideal generated by x squared plus 2 is indeed a field. Yeah, so that's kind of nice. Case 3, you got yourself x squared plus 3, so I plug in my 5 different values, I get non-zero for all, therefore irreducible. Therefore, if I mod by the principal ideal generated by this, I would have a field. And case 4, x squared plus 4, whenever you see something like x squared plus 4, you're working on mod 5, swap out that 4 for minus 1. It becomes more obvious what's going on, See, because when I plugged in 1, I got 0, right? So I'm like, oh, game over, it's irreducible. It's reducible. And of course that's obvious because x squared plus 4 is x squared minus 1, and that factors x plus 1, x minus 1. As you can see, that's a reduction of f of x into a product of factors, neither of which are units. Therefore, f of x is reducible. It's not irreducible. Now, problem 81, I think I essentially solve in the video, which I asked you guys to watch, and I'll talk about the solution here again, just a sketch of it, basically, but this is most of it, I think. And so the reason this is an interesting question is because two factors to 1 plus root 3 times 1 minus root 3, that's interesting. Not actually part of your homework problem, just saying, all right? And this shows that 2 is not irreducible if we're working in the extension of the rationals by the square root of minus 3. Now, why are these not units? That's the question concerning problem 81. Well, if we look at the norm of 1 plus minus root 3, which by the way is defined to be norm of a plus b root minus 3 is a squared plus 3b squared. You should look at page 155 to 156 of the 2018 notes to see that. Anyway, so this is 1 plus root 3, so apparently the norm of 1 plus the square root of minus 3 is 4. And, well, suppose we could factor it into a times b. Well, then the norm of ab is the norm of a times the norm of b, because the norm is multiplicative. And so in order to get a product of integers, which is 4, you have to have either one of them or the other of them is 1. Why is that true? It's because you can't have norm of a or norm of b be 2. Because if you look at the norm of a plus b root minus 3, in other words, a squared plus 3b squared, and try to set that equal to 2, there are no solutions. You can easily figure that out just by thinking about cases. If I have a is 1 and b is 0, I get 1. If I have a is 0 and b is 1, I get 3. If I have a and b both being 1, I get 4. So you see, and you can look at plus or minuses, the squares kill those, right? There's no way to obtain 2 from this. Consequently, there is nothing of norm 2, which means that the only way to factor the norm of two things, the product of two norms being 4, is for either one of them or the other of them to be 1. Which is, and then of course if the norm is 1, that means that the element's a unit. And as such, we have proved that any factorization of 1 plus root minus 3 necessarily includes a unit, which is to say that 1 plus the square root of minus 3 is irreducible in the context that we're working there. So that's a neat problem. Let's see here. Come on. Come on. All right. Problem 82. Let's see here. Come on. The paper is stuck. Here we go. Here we go. Here we go. So I got a bunch of problems about minimal polynomials in the homework, if you notice, which means odds of there being a question about a minimal polynomial on the final, I'd say, are high. All right. So let's talk about it. How do you find the minimal polynomial for a number? Well, there are various methods, but I mean, there apparently is an algorithm, but that's not taught in the course. And, I mean, I don't know it. My brother said there was one. I believe him. Proof by brother, right? So I is alpha minus 3. So I is the square root of minus 1. So if you square that, you get that, which gives us that minus 1 is alpha squared minus 6 alpha plus 9, which then gives me the quadratic alpha squared minus 6 alpha plus 10 equal to 0. So that leads me to claim that the minimal polynomial for alpha here is x squared minus 6x plus 10. Now we're working over the base field of R, and the question is this quadratic irreducible over R? Well, it's a quadratic, right? So if it has a 0, it's not irreducible. If it doesn't have a 0, it is irreducible. Is there a 0 of this quadratic in R? Well, no, there's not. Complete the square, and you can see that there is no real 0 to this quadratic, right? Therefore, m alpha of x is irreducible, and as such, this is the minimal polynomial for alpha. Because remember, a minimal polynomial for a number over a field, it's the polynomial, the monic, meaning leading coefficient 1, the monic polynomial of least degree, which takes the number as its 0. All right, so here's another one, root 2 minus root 3. I kind of expect something like this to be root 4 most likely, because root 2 and root 3 are independent in some sense. So here I isolate the radical, square that thing, FOIL it out, isolate the radical again. See, this is alpha squared plus 1 is equal to minus 2 root 3. I put it on the other side. Square both sides. That kills the radical. That gets you to alpha to the 4th plus 2 alpha squared plus 1 equals to 12, which indicates that alpha to the 4th minus 2 alpha squared minus 11 equals to 0 is a polynomial which takes alpha as its 0. And I did say in this problem you didn't have to sweat the irreducibility, which is good, because I think proving that this particular one is irreducible might be a little bit of a pain. Like, I don't think we can use Eisenstein criteria on that one. So anyway, you know, if you have a problem and you don't know how to prove irreducibility, do not despair. A good part of the partial credit, for a minimal polynomial question at least, would be just obtained from finding the minimal polynomial, right? So there's value in that. The proving that the minimal polynomial is irreducible is just the, you know, that's the complete thing. And sometimes that's technical. Sometimes finding the minimal polynomial is a pain. We'll see that in this homework. So here's homework 8. Started out with a kind of a nice warm-up problem, just like the last one. Find the multiplicative inverse of x, right, plus the ideal, which I'm going to call alpha. So I have alpha to the 4th plus 3 alpha squared plus alpha minus 1 equal to 0. This one's super easy. Set 1, put 1 on the other side, factor alpha out, there's your inverse. Done. All right, wonderful. Problem 86. So you're supposed to prove the formula that the degree of f over k is the degree of k over e times the degree of f over e, where e is an intermediate field, right? So if we drew a picture, it could look something like this. You've got your k, you got your e, you got your f, right? And so if this is degree n and this is degree m, then if we look directly from f to k, it's degree mn, right? So for example, if you do a degree 2 extension and then a degree 3 extension, in total you've got a degree 6 extension, 2 times 3 extension over the base field. The proof of that's in the 2018 notes, and it was shown in the video. So I'll let you look at those. Now, and it's essentially just, you know, beautiful linear algebra, although that's kind of redundant. What other kind of linear algebra is there? Let's see here. So let f be a field, and a and b be elements of the field a non-zero. C belongs to some extension field of f. Then prove that the extension of f by c is equal to the extension of f by ac plus b. So my approach here is to show that this is a subset of that, and that's a subset of this. That proves equality, right? Double containment proves equality. And my argument goes something like this. Since c is an element of f of c, and a and b are elements of f, which is by definition a subset of f of c, we find that ac plus b is an element of f of c, because of course the product and sum of numbers inside a field are again in the field. Thus, that implies that f of ac plus b is a subset of f of c. All right. Conversely, if we take ac plus b, a and b, elements of f of ac plus b, which of course we can do because a and b are in the f in the field, and ac plus b by definition is in the extension of f by ac plus b, well, that implies that c is an element of this. Because if these three things are in there, then c is also in there. I'll explain down here. But I'll come back to the star in just a second. So if that's the case, that implies that c is an element of this, which means that f of c is a subset of that, which means that we have equality of these two sets because that's a subset of this, and that's a subset of that. All right, this is a subset of that, rather. So to see the star, notice that A inverse times this, well, that would be in the field, right? But what is that? Well, that's the B's cancel and A's reduce, and you get back C. And of course, well, how do I know A inverse exists? Well, A is non-zero. And if it's a non-zero element of the field, then that means A inverse must exist. And consequently, we get the star, which gives us the necessity, the necessary equality that we want. So that is problem 87. Problem 88 is solved. I mean, the solution is given in the back of Galilean. I reproduce it here. Maybe not the same solution. I don't know. I mean, there's probably a few different ways to do this. To prove that these are not isomorphic as rings, you want to exploit essentially the fact that this ring has a square root of 3 in it, whereas this one, well, this might also have the square root of, does it have a square root of 3 in it? Maybe not. I don't know. Well, anyway, this one definitely doesn't have the square root of -3 in it. So this is a subset of the reals you can think of it that way. This, on the other hand, is not a subset of the reals, and it's got an imaginary piece in it. So you can basically focus on that and prove that you can't have an isomorphism, because that squaring to a negative number that will be allowed in this ring will not be allowed over there. And so you propose an isomorphism, and I decided to go from here to there. Just, I don't know, it's just more natural to me. And of course 1 maps to 1 and 3 maps to 3 because they're ring isomorphisms, and that of course also implies f of phi of minus 3 equals minus 3. But on the other hand, minus 3 is the square root of minus 3 times the square root of minus 3, and so we have this equals that by the ring homomorphism property, and preserves multiplication, right? And that is equal to minus 3, but look at this. You've got a real number times a real number equals to minus 3. Well, you can't do that in a subset of the reals. Therefore, it's impossible to have such an isomorphism. They're not isomorphic. All right, problem 89. Problem 89. So let's see here. Beta is a 0 of x squared plus x plus 2 over z5, then find the other 0. So students find these problems challenging at times, but there's really nothing to be scared of. We just have to work algebraically. All right? Now, I suppose in principle, one way to do this would be just to find the explicit zeros in z5 of this polynomial. I wouldn't recommend that. Instead, let's take this approach. We know that beta squared plus beta plus 2 is 0, and we are looking for alpha such that it's the other 0 of this polynomial, right? So by the factor theorem, it's got to be x minus beta times x minus alpha. We don't know alpha, but we'd like to find it. But we can work that out, and so multiplying that out gives me x squared minus alpha plus beta times x plus beta times alpha. And what we want, right, is we want alpha plus beta to be 1, or rather minus alpha minus beta to be 1, and we want the product of alpha and beta to be 2. Well, that immediately tells me that alpha is equal to 3 times beta inverse. In other words, alpha is equal to 2 beta inverse, all right? Because the product of alpha and beta is 2, that implies that multiplying by 3, I can, I get alpha times 3 beta is equal to 1. So that says that, again, alpha is 2 beta inverse in this context. Now, the multiplicative inverse of 3 is 2 in mod 5, all right? So, great. That's one answer, is that alpha is 2 beta inverse, but we can do a little bit better than that, because what is beta inverse? Well, beta squared plus beta is equal to minus 2, which implies that beta times 2 beta plus 2 is equal to 1. All right, again, I'm working mod 5. And as such, I have beta inverse is in fact 2 beta plus 2, so consequently, alpha equals to 2 beta inverse is actually alpha equals to 4 beta plus 4. That's the other 0. So there you have it. Now the text says to use long division, but I think I like my way. But anyway, there it is. But yeah, you could use long division. That would be fine. If you know how to do that, more power to you. Let's see here. Problem 90. We're supposed to show that if we take Q, adjoin, arbitrary roots of 2, is an algebraic extension, but it's not a finite extension. So first of all, notice that x to the n minus 2 is irreducible over Q by Eisenstein with p equals to 2. And it follows then that the extension by the nth root of 2, right, which we can look at as the quotient of Q of x. You can think of this as the quotient of Q of x by x to the n minus 2, if you like. I hope that's not too big of a jump. Let's see, Q of the nth root of 2 is up to isomorphism Q of x mod the ideal generated by x squared minus x to the n, rather, minus 2. And that's a field of degree. That's a field of degree n over the rationals, because, as I just said, Eisenstein gives us that x to the n minus 2 is an irreducible. So the quotient by that maximal ideal gives us a field, and that field has degree n over q. All right. But notice that that works for arbitrary n, right? Arbitrary n, woohoo! So that means every element in here is algebraic, which means that it's an algebraic extension. And but on the other hand, it is certainly not a finite extension because it contains the subfield, q adjoin the nth root of 2, which is degree n, right? Which means that the dimension of E is greater than n for arbitrary n, which means that the dimension of E over q is infinity. So of course it's not a finite extension. Another way to argue that more concretely is if it was a finite extension, then it would be an algebraic extension. And if it's an algebraic extension, then you have a polynomial which takes arbitrary roots of 2 as its zeros, which would mean that that finite degree polynomial had infinitely many zeros, which of course is nonsense. And all right, this one is nice. Problem 91 is real nice. Suppose that the degree of E over F is prime, and if you have any element in E, then either it's already in the field, so f of a is equal to f, or it gives you the entire extension field. There's no in between. So generally speaking, f is a subset of f of a is a subset of E in this context. So f of a is an intermediate field between f and E. And we have, by the intermediate field counting formula, a degree of E over F is the degree of E over F of A times the degree of F of A over F. So we're factoring a prime. If we're factoring a prime, well, that means that either that or that is 1. If this is 1, that means E is equal to F of A. If this is 1, it means F of A is equal to F. Right, there you go. It's not bad. It's not bad at all. Now, problem 92 is nasty. Problem 92 is a nasty, nasty problem. I don't think I intended to give you guys such a nasty problem. I didn't. I think it hadn't dawned on me. These cube roots make this just ever so unpleasant. So sorry about this problem. It is what it is. But if we, isolate the radical, cube both sides, we get this. And then I'm like, oh, well, that's no fun. How to eliminate the cube root from this? It's not immediately obvious. Probably need to take a different approach. So I tried a different approach. Let me show you what happened. This is what happened. So I finally come to my senses and I went, oh, wait a minute. The cube root of 4 is like the cube root of 2 times the cube root of 2. So these are not independent. In fact, these are like part of the same thing. In fact, if I look, like, the idea here is that the cube root of 4 is actually an element of the q extend by the cube root of 2, actually, right? Because it's just the product of the cube root of 2 twice. And since this has, as we were just talking about, the degree of q adjoin the cube root of 2 over q is 3. And of course we know that the degree of the cube root of 2 over q is 3 because the minimal polynomial is, literally x cubed minus 2, right? So it's a degree 3 extension, and because this is also in that extension, it stands to reason that we should be able to find a degree 3 extension. We should be able to find a degree 3 minimal polynomial for this if you think about the theory here. All right, I haven't completely explained that at the moment. I'm just saying. All right, now. So great. Well, when I saw that, then I'm like, well, if I isolate, I can write everything in terms of cube roots of 2, and then I can cube it, and that gets me to this, which then gets me to this, which then gets me to this, which then I can isolate the cube root of 4, and then I can cube it again, and that gets me to this 9th order polynomial, right? And I was happy. I found something that at least took this number as a 0, but I'm also relatively sure when I got to this point, it's not minimal, right? And I was right. So I called up my brother and asked him, hey, how would you show this thing's minimal? And so he did what any reasonable person would do, which is he got a computer and he ran it through something called Maple. And Maple, after a little bit of syntactical stuff, Maple spit out that this is the minimal polynomial, x cubed minus 6x minus 6. Now, I have not derived that, all right? But that is actually the answer here. Now, why is that? I haven't derived it, right? But here's some kind of intuition for it. It's basically built from a cube root of 2. The cube root of 2 has a minimal polynomial with roots. The other roots of the minimal polynomial are omega cube root of 2, omega squared, cube root of 2 squared, where these are the, omega is the third root of unity, e to the 2 pi I over 3. And you probably can derive it from playing games with like this, that, and that. I'm not sure exactly how it's derived, but that's a sketch. Obviously, this is an unfriendly question. All right. Problem 93. Some of these are very nice. Others of these are, well, unfriendly. Part A is very nice because we can solve this by Eisenstein. We look at it, 3 does not divide the leading coefficient, 3 does divide 9, 12, and 6, and 3 squared does not divide 6, therefore by Eisenstein's criteria it's irreducible over Q. Woohoo! So Eisenstein's where it's at. Now this one is unfriendly. So Eisenstein doesn't work here because the coefficients are 1, right? So usually you see something like this, you might think about a reduction over mod prime. So the trick here to use is that if we reduce the polynomial over a prime, over z mod p, then if it's irreducible over z mod p, it implies it's irreducible over z, or over q. And so z mod 2 is the way to go here, because so I'm working over mod 2, f of 0 is 1 bar, f of 1 is 1 bar, okay, so it's got no zeros. If it has no zeros, it must be that it can be factored into a product of a quadratic times a quadratic. Fun fact, x squared plus x plus 1 is the only irreducible quadratic in Z2x. So the only way this could be reduced is if it was the product of this irreducible and that irreducible. But when you multiply that out and use your Z2 math, you get back to x to the 4th plus x squared plus 1, which is not equal to f of x. F of x is reduction mod 2. So that implies that the reduction of f of x mod 2 is irreducible, and that, by the theorem, implies that f of x is irreducible. Obviously, this is a much more sophisticated argument than the Eisenstein one, right? Yeah. So if I was to intend for you to use the irreducibility by evaluation over a prime, it would probably be a degree 2 or degree 3 one, where we have the wonderful theorem that if there is a 0, it's reducible, and if there's not, it's not. So if we deal with degree 2 or degree 3, reduction mod prime is within the scope of the course, but I would say that if it's degree 4 or 5, it's okay for homework, but it's a little nasty for a test with a lot of time pressure. But, this might be separating the A's from the A pluses, this kind of problem, all right? Now, you're like, but Liberty doesn't give A pluses. Well, you got me. This one, easy. Irreducible by Eisenstein, p equals to 3, because 3 does not divide 1, 3 divides 3 and 3, of course, and 9 does not divide 3. So by Eisenstein, p equals 3, this is irreducible. Part D is, again, a nasty problem. Because it's order 5, which means I can't just use the 0 theorem. I have to look at reduction. So, but reduction mod 2 does work. That's nicer than working with like reduction mod 7, But anyway, so reduction mod 2, it has no zeros, so that must mean that this is a product of an irreducible quadratic times an irreducible cubic at best. And you can check that x squared plus x plus 1, which again is the only irreducible quadratic in Z2. By the way, that claim would make a reasonable test question. Prove that x squared plus x plus 1 is the only irreducible quadratic over Z2. I've asked that question on tests before in 421. But anyway, so you can check by like long division over z2 that this is not a factor of that. If you divide this into this, you'll get a non-zero remainder, which shows you that it's not a factor. And as such, there does not exist a factoring of this over. There does not exist a factoring of this over z2, which then implies that f of x is irreducible over q. Great. Part E is Eisensteinable. You just got to multiply it by 14. Take the least common multiple of your denominators, clear it out, multiply by 14, you get 14 g of x is this, and then you can do Eisenstein on this guy, because 3 does not divide 35, but it does divide this, and this, but 3 squared, also known as 9, does not divide 3. Therefore, by Eisenstein, 14 g of x is irreducible, which implies g of x is irreducible over q, and that's how you do it. Now, the last 3 problems are like taking candy from a baby. But to be clear, we're talking about a sleeping baby, because if you've ever tried to take candy from an awake baby, it's a different game altogether. Let's see here. Anyway, so I asked problem 94. It's like, what is the major theorem basically about prime ideals and commutative rings? What can you say about that? Well, here's the main thing I would say. I is a prime ideal of a commutative ring with identity R, if and only if R mod I is an integral domain. That is the big thing we can say. Okay? Problem 95. In a commutative ring with unity, what can you say about a maximal ideal? Well, the main thing about a maximal ideal is that R mod a maximal ideal is a field. Right? Or is field, if I omit my A and make me sound like educated brute. R mod I is field. There we go. Anyway, so there you go. There's that. And then problem 96. A field is a commutative ring with unity. That means every non-zero element's a unit, right? Quaternions, that problem 96 is about, are not a commutative ring since I times j is equal to minus j times I. Now, quaternions are interesting, though, in that every non-zero element in the quaternions is a unit. And not only that, the inverse for quaternions, you can calculate it essentially the same way as you calculate for complex numbers, right? Like 1 over z, what's the formula for it? Well, it's z bar over z bar. That is also true for quaternions. The inverse of a quaternion z, 1 over z, is in fact z bar over z bar. And quaternions are a beautiful, interesting example. In fact, the notation I hat, j hat, k hat for vectors that you see in calculus 3, for example, is in honor, in some sense, of Hamilton's quaternions, which were using I, j, and k, so-called versors. So quaternions simultaneously do dot and cross products. They're another formalism, in some sense, for three-dimensional coordinate geometry. And but it's kind of a lost art. People who love quaternions have a somewhat religious devotion to them, in my experience. I like them. They're interesting. My research is, roughly speaking, on an infinite dimensional analog of quaternions. Well, my thesis work, anyway. But anyway, it's been real. I hope this helps you.